Okay, welcome to this follow-up tutorial for getting started with OpenFoam. We're going to continue with this cavity tutorial that we began with last time. Just as a reminder, this is one of the three that is described in detail in the user guide, so you're welcome to consult, I believe it's chapter 2, section 2 in the user guide for additional details that so I won't be going over the entire tutorial in here, but we're going to start with this cavity tutorial, and I don't want to change or mess up some of the results that I did last time, so I'm going to go back to the directory where OpenFoam is installed and grab this same folder in the tutorial folder, the incompressible icofoam. We'll take this cavity, we'll copy it into the same folder that we had before, and I'm going to give this a new name, cavity 2. So we're beginning in a condition that was the same as where we began last time. Right? We're just taking the tutorial files, copied them into our working directory. And I'm going to open up a terminal here and start the OpenFoam program so that I have all the commands available, and I will go to cavity 2 folder, T2, and what we're going to do first is take a look at the solver again. Actually, let me just review what the steps we would need to take are. So the first, we would need to create our mesh based on our block mesh dictionary. And we'll use this command block mesh. So now we have our mesh files all built, and then we simply just run the icofoam solver. And now we've got the same time folders that were generated last time. These are the default folders. Obviously, we didn't change anything. I just want to draw your attention to each of these time steps. If we scroll up a little bit, let me maximize this. If we scroll up a bit, you notice there's no iterations, even at 0.4 seconds. There's no iterations in the solving for the UX, the X velocity. There's no iterations for the UY. There's not even any iterations for the pressure term. But as we scroll up, we start to see the pressure term have non-zero number of iterations, and then we got to scroll up a little bit farther to see the number of iterations change from 0 for the two velocities. So we're all the way down to 0.165 seconds here. So the first thing I'm going to do is open up the solver, and if you look at each of these steps, right, so it's solving for UX, it's solving for UI, and then it's in 2 steps, it's solving for P. So the question is, why are there 2 steps? And the answer to that is seen by taking a look at the system folder, and if we go into the solution, then we'll see this is where our solvers are described, and in this PISO entry down here, we need to specify the number of correctors. Right now it's set at 2. The second one is non-orthogonal correctors. Right now it's set at 0, and these 2 lines here, because we're using an incompressible solver, then the pressure magnitude does not matter at all. In fact, we can go and I didn't want to type that there. We can run pair view. And if I take a look at not the initial conditions, but any future time, and look at the pressure, cell value. And if I want to look at the magnitude of that pressure, forgot to use my, so the middle mouse button will translate the diagram, the right mouse button, and then changing the mouse or moving the mouse will change the zoom, and then the left mouse button is rotate. But we see the pressure goes from +4 to -4, and for an incompressible flow, the pressure does not matter. The absolute value of the pressure doesn't matter. It's just the relative change in pressure. And so when we go back into the system folder and look at this FV solution script, we're just arbitrarily choosing cell 0, which is going to be the bottom corner there, and we're forcing it to be a value of 0. If I change this to be 100, then it's going to take that same cell and assign a value of 100. So if we run this again, run OpenFoam, I've got to change directory. And we take a look at the pressure again. Rescale the values, and I put my color bar over here. Then I have the same relative change in pressure, but my nominal pressure in this case is 100 because that's what I specified it to be. So if you recall from one of the homework problems where we looked at the square annulus, we had all Neumann boundary conditions. In other words, we had, from a thermal standpoint, that last homework problem, we had insulated boundary conditions on the outside edges, and then flux coming into the channel from the inside square. And those are, because those are all Neumann boundary conditions, then we have to specify a temperature somewhere. And what you should have found is that whatever you started with your initial conditions, that tended to be the nominal temperature on the inside the flow. But if we take one of those cells and replace its equation, forcing it to have some temperature, then it pins down the rest of the field inside the flow. So the same thing is happening here with pressure. And if we had a compressible solver, then we wouldn't have this option, because we need to, the absolute value of pressure is also important. So if we go back in, let me open this back up. And so we have that now set at 100. We could change the reference cell, not that it matters in this case, but if there's some other cell we want to specify its pressure, then this is where we would change that number. If I change this to 4 and this one to 2, and let's just run this one more time. You'll see that each time step now, it's going through the same process. It's solving for UX. It has a beginning residual, final residual. So this last time step, just as before, there are no iterations. But you'll see the pressure corrector and then the pressure equation calculation. We specified 4 loops. Let's open this back up. So the number of correctors we have as 4, and the non-orthogonal correctors we have as 2. So the non-orthogonal correctors is always going to be at least 1 per loop. So this first number that we input is 4. This is kind of the outer loop, 1, 2, 3, 4. And then this non-orthogonal correctors, this is additional inside loops that we would take. So we're always going to take one of those inside loops, but here we're specifying 2 extra inside loops. So that's why each of these outside loops you see 3 calculations of the pressure. So, and this is again not going to affect the accuracy of the solution, it just affects the path to the solution. So it, in this case, it's such a quick simulation, it doesn't really matter, but in other scenarios, it might be advantageous to us from a convergence standpoint to get solutions quicker, to change these numbers, but it shouldn't affect the overall accuracy. The discretization scheme is going to affect the accuracy. So let's put this back to 0 and 2. It's back to 0. Okay. Let's take a look at the mesh resolution. So as you recall in the, I don't want to be in system. If I go to the constant folder and look at the polymesh folder, and I want to open the block mesh dictionary file. So here is where I specify what type of mesh. So I have a hex element, and for every hex element I need to define 8 points. So here's the 8 points that I list here as the vertices, and I say my hex element is comprised of those same 8 points, and then I specify how many elements in each direction, and then in this case I have a simple grading, so it's uniform in all directions as well. If we change this to 40, actually before I do that, let's take a look at the velocity results real quick. Look at the velocity, do surface with edges. So my velocity magnitude here, we know that the top wall is moving at a velocity of 1 meter per second. So we know that nothing is going to be higher than that number. And so this makes sense from a back of the envelope calculation standpoint, that our maximum velocity goes from 0 all the way up to 0.852. Let's see what happens as we change the number of elements. Constant, and then poly mesh gedit. So if we change this to 40 and 40. Oh, another thing I wanted to draw your attention to is when as it's solving this each loop, it's reporting all these residuals, but it's also reporting this current number. So the average current number and the maximum current number. And again, this is defined as the time step, the product of the time step and the velocity magnitude for each cell divided by the size of the cell. And again, we want that to be less than 1. So for all these time steps, you'll see we're meeting that, we're less than 1. But as we change the mesh resolution, then we might see some different behavior here. Actually, I'm just going to come in here real quick. Let's keep it open. Okay, so if we run the solver again, we still have a current number less than 1 for all these cases. And we can take a look at the velocity results. And it didn't change much, even though we have, it doesn't look like we did 40. No, it's the same. Yeah, this says we only have 400 cells. Did I not save that? Oh, yeah. I didn't run the block mesh again, right? So I need to run my function block mesh. And now I've created new mesh files based on the change in the number of cells that I specified in the dictionary file. And I should be able to then run the solver again. And now when I open up Parafoam, yeah, now I've got a lot more elements there. Well, 4 times as many. And not surprisingly, the velocity is increasing. We have a finer resolution. It's still not greater than 1, so we're confident that the results, at least good from look good from a physical standpoint. If we go back to each of these time steps, we'll see that the mean current number is well below 1, but we're starting to see some peak current numbers, and most likely these are, since the delta time is the same and my mesh is uniform, that means my delta x is the same. So it has to be, the current number is maximum where the velocity is the highest, so right near that wall. But we still are iterating and finding that we have, small residuals below our cutoff criteria, and so the solution is not blowing up. But if we change this to be $400, for example, and we come in here and we have to run our block mesh utility again. Takes a little bit extra time now because we have so many cells. So we have 160,000 cells. And we run our OpenFoam solver again. Here we are on the first loop. So looking at this residual, we start with an initial residual of 1, we go down to 0.002. This is not below our cutoff criteria. It has simply reached the maximum number of iterations. So we could go in and change that. But the bigger problem here is that each time step, this is going to do a core dump here in just a minute, I'm sure, but my mean current number and my maximum current number are well above 1. And if you look at the residuals, they are increasing, right? That's always hitting 1,000 iterations, and my residuals are increasing in these, for the velocities at least. So we went from 2e to the minus 3 to 80 to the minus 3. So this next step for our x velocity is now almost 3e to the minus 2. And again, hitting the 1,000 iterations in each case. So at some point it's going to do a core dump, because what's happening is the residuals just keep getting larger and larger and larger. And I'm not sure exactly when that's going to happen. But you see the current number now is increasing too. So what's happening is the velocities predicted near that moving boundary are becoming larger and larger and larger every time we do a time step, which is obviously bad. Let me just kill this actually. And there should be some region where depending on the size of our mesh. Let's try 100. So you see the residuals are continuing to decrease. We're not hitting the maximum number of iterations. Actually, the current number keeps increasing here as well, doesn't it? So here's my core dump. So by the time we got to even 0.085, we have a mean current number of 118, a maximum of over 400. And then the very next time step, we get to current numbers that are insanely large. So let's try 60. Okay, so we successfully made it through that one. The current number, the maximum current number, is not ideal. The mean is still below 1. Our iterations are behaving nicely, meaning we have a final residual that is either below our cutoff criteria each case, or at least keeps on decreasing. But let's take a look at the results here. So we're starting to see velocities that are approaching 1. They're still not equal to 1. A slight increase in our mesh count would change that, maybe up to 80 or so. Iterations are still below 1,000, so we're not hitting the limit there. And our current numbers are the mean. So we still the residuals behaved. The mean and the max current number are well outside of the acceptable range. So if we take a look at this in pair view, then I mean the pressure, velocity. So we had something that was numerically stable, but it's giving us bogus results. All right, so we need to be mindful of that current number. And the way to fix that, if we want this size of a mesh, then we need to come in here. Well, not in this file, but let's say we want let's do 80. So we multiplied the mesh in each direction by a value of 4. So we have 16 times as many elements. What we're going to need to do is come into our system folder in the control dictionary file, and we have our start time and end time, but this delta t now we need to change. So since we changed it by a factor of 4 in the x, let's change this by a factor of 5. But because I changed that as a factor of 5, if I'm simulating the same amount of time, then I have 5 times as many time steps that I'm going to encounter. So instead of every 20, I'm going to just write every 100 time steps. So I'll have the same time directories at the end of the day, but it represents 100 time steps in this scenario. So if I solve this now and I come back to here, I don't have to do block mesh again because I didn't change the mesh, but I did change the solver criteria for time. So if I run this again, you see that it's much faster. The number of iterations per time step is much smaller as well. It's going to take a little bit more time because I have many more time steps to consider. But my current number now is perfectly behaved. And if I take a look at the results, then they behave perfectly. In other words, we can trust these numbers now. So there's a number of things to watch, and it's not just whether or not your solution blows up, it's the current number, for example. So this will be reported for every time step, and you want to monitor that. You want to monitor the residuals, the number of iterations. I think the maximum right now in the settings is 1,000, so if you're reaching that, then more than likely you're in a condition where you're going to get bogus results, because we should be able to get our residuals down to an acceptable level within 1,000 iterations for sure. Okay, another thing I wanted to show you real quick in pair view was the plot line command. We can take any of these icons up here represent additional analysis tools that we have. So the one I'm going to show you here is the plot over line. And if we want to, as soon as I click that, I don't know if you can see this, but there's a cursor here, and there's another cursor down there that you can't quite see. So this is my line, right? So if I want to look at my line at these locations, here's the points that are specified, and I want to look at the velocity or the pressure as a function of location on that line, then I can create myself a plot to do this. So this represents the velocity and the pressure. I can come down here and I can, for instance, maybe I'm not interested in pressure, I'm only interested in velocity. This one's the velocity magnitude. These are the components of velocity, so maybe I'm interested in the x velocity and the y velocity as well. And more than likely, you're not just going to make some arbitrary line. You're going to specify points that make sense. So let's take this right through the center. So we'll go 0.05 in the x, 0 in the y for our first point, and then halfway through my z would be this, and we'll have the same x. So this is going to be a vertical line, and we'll go up to the top of the domain, which is 0.1, and the same z. So now my line is directly through the center of this, and this is what the behavior looks like. So here's my my y velocity, here's my x velocity through that line, and then here's the magnitude, which is just the square root of the sum of the squares of each of those two components. I can then export this or save the data. I can change the format to any of the ones that are listed here. If I choose CSV and call it data. Right. So I can change this from points to the cell values. I'm going to leave it as points for now. And down here I had a resolution of 100 points. So if I wanted 1,000 points in there, then I'll have 1,000 data points. In fact, let me do that. Let me save over my previous one. And then if I come in here, I've got a data CSV file, and it gives me pressures and velocities. Let's open this up in LibreOffice. And that's a good import. So here's my pressure, here's my x component of velocity, here's my y component of velocity. This is my arc length. I don't have any masks or and I don't have any z velocity, so I don't care about that. This arc length represents the distance along that line. This was a vertical line, so it's not surprising that I mean, my x is the same for all points, so I don't need that one. And it's not surprising that the arc length numbers are exactly the same as my y location, because I have a vertical line. So I can get rid of this, and my z locations are all the same as well. So here's my pressures, my velocities, and then if I want the magnitude, then it's just going to be the square root of the sum of the squares of each of these. So now I can plot these, and I can do GCI studies, for example. If I wanted to look at the maximum of the x velocity, for instance, I could take any of these points here, maybe the minimum of my x velocity, or the maximum of my magnitude, or maybe I could even take a look at the y. Maybe the y velocity is the one that I care about. Maybe I want to do a GCI study on the peak value found from this, and by specifying this line to be 1,000 points, I can make those same 1,000 points for any and all mesh sizes, and what it does is it's going to give me an interpolated value if it doesn't fall in a cell center, obviously, which is fine. I just need to be cognizant of the fact that introduces some additional error. But if your mesh count is high enough, then that's going to be very small compared to it's going to be a small effect in the GCI study. Okay, so if you go to the user guide here, talk about the mesh, or let me go back to the tutorials here. So this is our lid-driven flow. We basically gone through a lot of this. Here's our current number definition. And then you'll see that it goes through a number of modifications to that, starting with this one, 2.1.5, increasing the mesh resolution. You can play around with some of these. These are stream tracers. So that's another thing you could maybe look at. You could look at the vorticity, right? The maximum vorticity in this flow. Maybe you use that as a validation variable for your GCI study. So you can walk through the rest of this on your own. I just wanted to draw your attention to a couple of modifications they do. The mesh grading. In order to do the mesh grading, meaning we don't want a uniform mesh, then they break this up into 4 different blocks, right? And now we can assign a certain type of mesh definition to each of these blocks uniquely. And then the next thing they do is increase the Reynolds number. So you're going to see a change in the for high Reynolds number flow. We're going to need to do change some of the foam settings and introduce turbulence models. And then if we wanted to change the case geometry, in this case, what they're doing is they block out one of the 4 blocks, and hopefully this looks familiar enough to you that you should appreciate what's going on here. If you do the annulus problem that we've talked about in class, or done the homework on, then this is basically a 1/4 model of that. You obviously need to change boundary conditions. So you'll have a bunch of no slip conditions and then velocity in the z direction into the page. But go through the rest of this tutorial. They misplaced this figure. I know that they went and they start the next tutorial on stress analysis of a plate with a hole, but this figure belongs to the cavity solution. So they call this cavity clipped. So go through that. This will be this one in particular would be useful for you. The next homework will have a problem in OpenFoam or Star, depending on which software you've chosen, to do this same annulus problem. So all right, the last thing I want to draw your attention to is let me go here actually. So if I go into the installation folder for OpenFoam, if I come to applications and then solvers, incompressible, here's my icofoam. So this icofoam.c is the code that is solving the differential equation of interest for the icofoam solver. And so the first thing it does is it's going to read these pisocontrols.h file, which and then the current number. There's a number of settings built into the create fields, which it's going to go and read the transport properties file. It's going to read the initial conditions, and then run the icofoam solver, which is right here. The main thing I want to draw your attention to is this FV vector matrix equation. This is basically the definition of the differential equation that we're solving here. So we've got a time derivative, this ddt, and then we've got the divergence of phi, and then we have the Laplacian of nu with velocity, and we're going to set all this equal, this u equation, we're going to set it equal to the negative gradient of pressure. So this is, if you look at each of the solvers, then you'll see this section where they have different terms. If it's compressible, then you'll see an additional equation for pressure. But just to give you an idea of in the event of if you need to change the solver or modify the solver, the first thing to do is make sure you copy it from the installation folder to some other location so you don't mess up the main solver for all other OpenFoam simulations. But this is where you would tweak it if you needed some extra terms in there. So perhaps you had some heat generation due to irradiation, for instance. You had some uranium particles in the flow, or there's no real limit to what you can do with this. It's just a matter of understanding the solver files. Okay, so that concludes this second session. You should have enough to get going on the next homework once it is assigned. It will be all based in OpenFoam or again Star, depending on which software you chose. And we will begin with a discussion on turbulence beginning next week. Thanks.